Okay, by request, we'll talk about a few of the review problems that we were not able to get to in class today. First, let's talk about problem number 4, which was to figure out the prime factorization of, let's see if I can get this pen to work, 4 million, let's see, where's the number, 700,619. Okay, so we've got the handy dandy calculator here to help us with this. First, we notice that if we add the digits here, we get 4 plus 7 is 11, plus 6 makes 17, 18, 27. So that's a multiple of 9, and so I know that if I divide it by 9, I should get an even number. So that works if I divide it by 9. If I take what's left here and take 7, 9, let's see, 7, 9, 11, 20, 21. So that's a multiple of 3, and so this should be a multiple of 3, but it should not be a multiple of 9. So if I divide by 3, I get the next number, but if I divide by 3 again, it does not work. Okay, so let me clear that out. So I've divided it by 27 so far, so that's equal to 3 to the third. If I can get this to work. Times. Okay, now let's go to see if we can figure out what the next digit is going to be. Well, there's no other royal way to this except trial and error and hope that something works. Let's try 7, and fortunately that works. Let's try it again. It works again. Try it again. It does not work, so I can pull out 7 squared out of this. So we get 7 squared. Okay, now notice that the 11 trick here is going to work this time. If I go 3 minus 5 plus 5 minus 3, that's 0. And so I know that 11 will be a factor of what's left here. So 323. Okay, now we're getting to somewhat more manageable numbers here. 323. Now notice that the square root of 323 is 17.9. So that means that I can try every prime number less than or equal to 17. If none of them work, then I know that 323 is prime. So if I divide by 11, it does not work. If I divide by 13, it does not work. And dividing by 17, well, it does work. So 17 times 19, and that is the complete prime factorization. So 323, the square root of that number was just a hair bigger than 17, which means I only need to check the prime numbers less than or equal to 17. If any of those did not work, if all of those did not work, then we would have known that 323 was prime. Okay, so that's problem number 4 on the review. Let's now turn our attention to problem number 14. So let me get rid of this. And so what I need to show is that, so if, whoops, if I have integers a, b, d, m, and n that are all integers, then d divides a implies that d divides ma plus n times d. I barely got that in. Okay, so let's think of the proof of this. So proof. We know by assumption there is an integer q so that a is equal to d times q. That's just the definition of what it means to be divisible. So m times a plus n times d is equal to, well, let's see, we have m times d times q plus n times d. Okay, now I'm going to do this very, very carefully on the steps here, and I'll say out the steps. I don't have room to write them down. But by associative property, I can write that as m times d times q plus d times n. By the commutative property used twice, I get d times m times q plus d times n. By associative again, we have d times m times q plus d times n. And then by the distributive property, I can factor the d out. There's m times q plus n. Now by the closure property, we know that m times q is an integer, and therefore m times q plus n is an integer. And that's by the closure properties of multiplication and then division. And so we conclude that d has to be a factor of ma plus n times d, because the thing in parentheses is an integer. So that's the end of the proof. Now for test purposes, I might ask you to list out every step. If I don't ask you to list out every step, then it would be simply fine to just simply factor the d out and go directly from here to here, and then note that the thing in parentheses has to be an integer. Okay, so that's this one. I'm going to stop the video here, and then I'll do the next two problems on the next video.